Hello everyone, I'm Chongwen. The focus of this talk is to optimize packet processing programs written in the Berkeley Packet Filters (BPF) framework. BPF is an emerging technology to do customized and high-performance packet processing. It's been widely used in industry. Facebook uses BPF for high-performance load balancing. Google uses BPF in its Kubernetes clusters. Recently, a few companies came together to launch the BPF Foundation, showing their long-term investment in this technology. So what is BPF? Modern BPF is a general kernel extension mechanism. It's extended from classic BPF, which was used to write packet filters. In this talk, when we say BPF, we mean the extended version. Users can write and attach BPF programs to different points within the kernel to process packets. BPF programs can be loaded in the system core, socket and TCP/IP layers, traffic control, the network device driver, smart NIC, and so on. Within the kernel, BPF programs run in a virtual machine with basic instruction set. The virtual machine has 11 registers and a stack. BPF programs may use key value maps that may be shared with other BPF programs and with other user space processes. BPF programs may also call help functions to invoke specific functionality, which is baked into kernel's code. This is the workflow of a BPF developer. Suppose our target is to write and execute a BPF program in the network device driver. First, we can write a BPF program in C and use client to compile it into BPF bytecode. Then use a system call to load the bytecode. The bytecode will be checked by the kernel checker, a component in the kernel that ensures the safety of bytecode. BPF enables unprivileged user code to run directly in the kernel context. Hence, the checker is crucial to ensure that malicious or bugging user code cannot crash the operating system or leak any privileged data. The checker proves safety by doing a static analysis over the bytecode. If the bytecode is accepted by the checker, a JIT compiler within the operating system will convert it into native machine code. Finally, the program can be executed within the network device driver. But it's not easy to develop high-quality BPF programs. There are two reasons. The first problem is size. Because the kernel checker must verify a program safety quickly, the kernel bounds the number of instructions it examines for each program. On modern kernels, the limit is 1 million, including examining the same instructions across different code paths. In practice, even a program with a few thousand instructions may be rejected. To get such programs accepted, a developer must disable some features or refactor the code. The second problem is about performance. We'd like BPF programs to have excellent performance. Because at high rates, even small improvements can lead to significant CPU cost savings. One approach is to have developers manually optimize BPF bytecode, but it requires developers to be familiar with BPF. If the program is long, this is painstaking work. Another approach is to use compiler support for optimization. However, this is lacking today. For the benchmarks in our experiments, higher optimization flag 03 produces the same code as 02. This isn't because 03 is already amazing. We have identified several optimizations over 02 code. This is the problem statement of our paper. Can we automatically produce compact and more performant programs? The key challenge is the tension between performance and safety. The kernel checker is stricter than needed. The checker's static analysis has many heuristics baked in to reduce the number of cases it needs to consider, and hence reduce the time to check the program safety. So a program that's in fact safe may be spuriously regarded as unsafe by the checker. Here's an example. This program stores 2 bytes on the stack. However, it's rejected, since according to the checker, stack access should be aligned to the size of access. If we modify the store address, it will be accepted. The tension with safety makes it challenging to design compilers to optimize code. Traditional compilers match patterns over small portion of code and rewrite them into efficient code. In this example, the first instruction sets memory as 0. The second one sets the next memory as 0. We can design a pattern to optimize these two writes into one write. However, such optimizations are frequently incompatible with the checker's constraints. Recalling the stack access alignment example we showed before, this optimization will be rejected if the stack access is not aligned to 2. Every potential optimization must also consider safety, since such safety constraints apply to many optimizations. Being conservatively safe precludes many optimizations, while optimizing aggressively risks program being unsafe and hence rejected. We call this the phase ordering problem of BPF compilation. Developing better optimizing compilers requires considering both optimization rules and safety constraints. We design and implement K2, a BPF optimizing compiler, which takes client-compiled BPF bytecode as input, produces drop-in optimized bytecode. Over a set of realistic benchmarks, K2 improved code size, packet processing latency, and throughput relative to the best client-compiled programs. K2 leverages stochastic program synthesis to optimize programs. K2 provides formal correctness and safety guarantees. We do this by encoding the BPF instruction set in first-order logic. K2 formally checks equivalence between BPF programs and safety predicts over the program using logic. We introduce several domain-specific techniques that reduce equivalence checking time by 6 orders of magnitude compared to naive formalization. Our formalization can encode practical BPF programs. It handles arithmetic and logic instructions, memory aliasing, control flow BPF maps, and helper functions. You can see the details in our paper. Next, I'll unpack why and how K2 uses stochastic program synthesis. Program synthesis is a search procedure that automatically generates a program satisfying a specification. Our specification is complex, combining correctness, safety, and high performance. By considering them together in the search, we address the phase ordering problem. Stochastic synthesis is a randomized algorithm to explore the space of programs based on MC-MC method. The search is guided by a general cost function evaluated over programs. This is not the state-of-the-art approach to synthesis. However, compared to other approaches we considered, it's fast and generalizes easily to BPF optimization. Stochastic search can handle complex costs with complex constraints. At a high level, K2 takes a BPF program as input and produces optimized BPF program as output. The given input program is the first program for K2's stochastic search loop. At each iteration, K2 performs a small random modification to the current program to generate a new program called a proposal. K2 computes the cost of the proposal. The cost is a combination of correctness, safety, and performance. If the proposal's cost is at most slightly larger than the current program, it will be accepted. The proposal becomes the next program used as the base for modification within the search loop. Whenever the proposal is accepted and its safe equivalent, it will be added into a program database. After a configurable number of maximum iteration, K2 will rank all the programs in the database and emit top K programs according to performance. These programs are all correct, safe, and have the best estimated performance. K2 makes several domain-specific contributions. We propose several program modifications to generate proposals, reducing the search time to find better programs. As part of cost computation, we introduce techniques to check equivalence of programs with pointer aliasing, control flow, BPF maps. K2 introduces several optimizations to check equivalence faster. Notably, we propose methods to check a small window of the program while still being aware of the program's context within the program. K2 is the first work that proposes and leverages safety counterexamples, a fast method to prune unsafe programs using test cases. So how well does K2 work? We evaluate K2 in terms of two performance goals: program instruction count reduction and program performance improvement in terms of latency and throughput. We use K2 to reduce the number of instructions in 19 benchmarks. Here's a part of results. We compare K2's results with the best client version. The comparison ranges from 6 to 26%. The average compiling time is about 22 minutes. This table shows the throughput improvement of 6 benchmarks running in the device driver. Gains range from 0 to 4.75%. We measured average round-trip latency for 4 benchmarks running in the device driver. The reduction is from 1 to 55%. Why does this work? To understand the evaluation numbers, we cataloged optimizations that K2 derived automatically. You can find a detailed list in the paper. Here are 2 optimization examples found by K2. The first example combined 2 writes into 1 write, reducing 2 instructions. The second optimization compresses the program, leveraging the context of the window within the program. K2 used the value of R3 written in a prior instruction to optimize the window. In summary, we presented K2, an optimizing compiler that produces programs with reduced size and higher performance. K2 contributes several domain-specific techniques for the synthesis and verification of BPF programs. Looking forward, we believe that synthesis is a viable approach to optimize packet processing programs. Thanks for your listening.